All right. Hello, my name is Jared Brzenski, and this is my work with Dr. Johnny Corbino and Professor Jose Castillo on building a mimetic coastal ocean model. There are many different ocean models, and why do I think we need another one? First, by using mimetic operators, we can simplify the numerical schemes used by the ocean model. Ocean models have many different numerical schemes based on conditions or features that you want to capture, and mimetic operators have been shown to work on other difficult PDEs, especially advection diffusion problems with alternating flows. And their features guarantee accuracy up to and including the boundaries, right? The mimetic operators eliminate having extra schemes to deal with points near the boundary, and they're built with a predefined order of accuracy. So increasing the order of accuracy is simple compared to coding a new numerical scheme. For curvilinear coordinates too, oceans and ocean models have things like steep gradients in them, like undersea ridges or cliffs, that are an issue for regular coastal ocean models using finite difference methods. By using curvilinear coordinates, though, all work is done on a logical domain that is topologically equivalent to a cube. So things like boundary conditions and interpolation are very simple to implement, very accurate. And computational efficiency, right? Finite differences are the fastest methods for solving PDEs, and using mimetic operators, which take the form of matrices, ensures that all calculus operations are inherently computed as matrix vector operations, which computers are optimized to calculate. So mimetic operators are discrete finite difference representations of the gradient, divergence, and Laplacian operations from calculus. I use the operators from a library called MOL, the Mimetic Operators Library Enhanced. And what they do is allow for simpler coding when calculating these operations in MATLAB or C++. They're built with a specific order of accuracy by the library, and that accuracy is preserved all across the domain. So to solve the Navier-Stokes system, all calculus operations are replaced with their equivalent mimetic operator. Computationally, these are represented by matrix vector operations. And this replacement is replicated to all steps taken to solve this nonlinear system. Right? All calculus operations are replaced with whatever mimetic operation is needed. And outside of the RK3 time scheme, all operations here are matrix vector operations. There are no for loops in this code. There is one system that needs to be solved, the Poisson equation here in the middle, and by far is the most computationally expensive step in the process. We tackle that too. So the coastal ocean model is implemented in C++ and leverages a super LU library for solving the Poisson system. It is by far the most time-consuming part, with the original code taking 99.9% of the computation times. So using the mimetic operator for the Laplacian and knowing the left-hand side of this equation never changes, I found that some modifications, super LU, and by extension LAPAC, can save the decomposition of this left-hand side, and more importantly, save it in a sparse format to reuse in later steps. And this gives significant gains to the overall computation time. Simulations that one took days can now be done in minutes. So this chart here is showing the speed for one solve of this system. And with 10 million cells, the previous solver solution technique took 27 minutes, and it's now done in 14 seconds. The ultimate application for this model is modeling internal waves interacting with bathymetric features in the Monterey Canyon system. There are many questions that can be answered through high-resolution 3D modeling, like locations and intensities of internal wave breaking along shelves, or analyzing the dissipative rate of internal bores in the canyons. But for the model to be complete, additional features like buoyancy, salinity, subgrid stresses need to be calculated and added to the model. These features and much more are discussed on my poster. Thank you very much.